This is problem 16.71 on page 1151. A bowler projects a 5 or 8-inch diameter ball weighing 12 pounds along an alley with a forward velocity v naught of 15 feet per second and a backspin omega naught of 9 radians per second. Knowing that the coefficient of kinetic friction between the ball and the alley is 10%, determine A, the time t1 at which the ball will start rolling without sliding, B, the speed of the ball at time t1, and C, the distance the ball will have traveled at time t1. So let me sketch the problem over here first. So the bowler projects the ball, and eventually, of course, it contacts the alley. Got an initial speed of 9 radians per second and an initial forward velocity of 15 feet per second. Now, if you're trying to figure out what will happen, eventually this ball will start to slide on the alley. The alley will apply a force like this, causing the ball to slow down because it's rotating backwards, and it will eventually start rotating forward. Okay, and that's the time we're interested in, when the ball is rotating forward with no slip. Okay, so the coefficient of kinetic friction, since it's slipping, is 10% between the alley and the bowling ball. The mass of the bowling ball is 12 pounds, and the diameter of the bowling ball is 8 inches. Now, it's convenient to write the diameter, or better yet, the radius in terms of feet. So that's a third of a foot, because half of the diameter would be 4 inches, which is a third of a foot. Okay, so that'll give us the radius of the bowling ball. So what I did first is set up a free body diagram and a kinetic diagram. So here's the bowling ball. Obviously, there is a normal force from the lane onto the ball and weight. But once the ball contacts the lane, which it'll just keep doing exactly what it's doing until it hits the lane, once it hits the lane, there will be a friction force as well. Okay? I'm going to use a coordinate system set up in the typical fashion. Now, the kinetic diagram looks like this. It's pretty simple. Mass, acceleration in the horizontal direction, mass, acceleration in the vertical direction, and I alpha. Now, we know the acceleration in the vertical direction is 0 once the ball hits the lane. We're assuming the ball just comes down, lands nicely on the lane, and just continues along. Okay? All right, so the next thing to do is to set up the equations of motion. So if we continue, we can sum forces in the vertical direction, but we know that the ball is just rolling along the lane or sliding along the lane. It's not accelerating in the vertical direction. So we know that the normal force minus the weight force equal the mass times the acceleration in the y direction. Well, that's just 0. In fact, it's the sum of forces in the vertical direction equation that would tell us that this acceleration is 0 just based on the way the ball moves. So basically, the normal force equals the weight force. A pretty trivial result. We have two other equations in a planar problem like this: sum of forces in the horizontal direction and the sum of moments equation. We sum forces in the horizontal direction. It's pretty easy. It's negative F. That's it. Friction force is the only force acting horizontally, and it acts opposite to the x direction, so it's negative F, and that would be equal to the mass times acceleration in the x direction. The last equation is to sum moments. Now, we can sum moments about many different points. Probably the easiest is to sum moments about the center of gravity. So that's what I'm going to do. Summing moments about g, taking counterclockwise as positive, which makes sense because it has the positive z-axis. What would we have? Well, the moment of all the dynamic forces go away, we'll end up with I alpha. But what force does not pass through g? Only the friction force. And the friction force will cause a negative moment, because if we're summing moments about g, notice the friction force tends to cause a clockwise rotation, which is a negative direction moment. So we need force times radius, where radius is the radius of the bowling ball, the sphere, and it equals I alpha. Okay? So there are the three equations of motion that we have. We might also need a kinematics equation. We might need to know, for example, about a relationship between the acceleration in the forward direction and the angular acceleration. The only problem in this problem is that there's slippage. If there were not slippage, then there'd be more of a relationship. But anyway, I'll let you continue the problem here. So now that the equations are set up, it looks like we've got quite a bit of work to do. For example, is there a relationship between the friction force and the weight? No. There's a relationship between the friction force and the normal force, right? That's the way friction works. The way it goes is friction equals mu N. Now, it's true that in this particular case, the normal force and the weight force are equal to each other, so we can continue this and write that this is equal to mu W, or mu mg. Okay, but that's just because of the nature of this problem. Okay? So if we were to replace the friction force with mu W or mu mg, we would have equals negative mu mg. And so that tells us that the acceleration in the horizontal direction is just equal to negative mu g. In other words, the bowling ball is accelerating that way. That makes perfect sense. Okay? So we can figure out what that number is. We're in English units. 10% of 32.2 is just, well, it's negative 3.22 feet per second squared. So now we know the acceleration of the bowling ball in the horizontal direction. Okay? And that was summing forces in the horizontal direction. What about if we use this information to continue the sum of moments equation? Because we pretty much used up the sum of force in the vertical direction equation. Well, the negative friction force is just MAX, isn't it? So I could just write MAXR equals I alpha. By the way, the moment of inertia of a sphere, you can look that up in the back of your book as well, it's 2/5 mr squared, where r is the radius of the sphere. So that means we can substitute for I. In fact, let's rearrange a bit. Alpha equals MAXR over alpha, or I'm sorry, over I, pardon me. And so this would be m, acceleration in the x direction, r divided by 2/5 mr squared. Look what happens. Well, the radii go away, the mass goes away, and we can write that the angular acceleration then is 5/2, converting and multiplying, times ax, negative 3.22 feet per second squared, divided by, the only thing left is the radius, which is 1/3 of a foot. What 4 inches are is 1/3 of a foot. So the feet go away, 2 feet. Plug all this into a calculator, and you'll find that the angular acceleration is negative 24.15 radians per second squared. So now we have the linear acceleration of the bowling ball and the angular acceleration of the bowling ball. Okay? This comes from the equations of equilibrium. Now what kind of problem do we have? Now we've got to study a motion problem, don't we? Because the question is, how long until the ball no longer slips but rolls without slipping? At that point, what's the velocity and how far has it traveled to get to the point where it's no longer slipping? Point 1 is a very important point. It's where the ball is rolling without slipping. Okay? I didn't write that on the board to take too much space. But now we know how the ball is accelerating both angularly and linearly, and we can answer these questions. So now we have a kinematics problem. Okay? So now that we've got the accelerations, all we need are kinematic equations to tie everything together. So let me jot down what we've discovered. The acceleration of the ball in the horizontal direction is negative 3.22 feet per second squared. You already know what coordinate system I'm using, so I don't think we really need that anymore. The angular acceleration is negative 24.15 radians per second squared. So that's everything we need to know. Notice that those two accelerations are constant. Therefore, we can use constant acceleration equations, or equations derived from constant acceleration, to work with them. For example, the angular speed of the ball will be the angular speed initially plus the angular acceleration times however much time it accelerates. What am I saying here? Well, think about it this way. We know the initial rotation rate of the ball, and once the ball is rotating without slipping, it's going to be related to the forward velocity. As a matter of fact, it would be related as follows. The velocity in the forward direction, the linear velocity, would be the negative of omega 1 times r. In other words, when it's rolling, when the ball is rolling without slipping, the angular rotation rate, omega 1, will be related to the linear translation rate, v1. Now the reason it's negative is because if you think about it, really this is v equals omega cross r, okay? And so if you take the cross product, you realize that a positive velocity means a negative rotation, you see? So that's where the negative sign comes from, is just the cross product. However, there's another constant acceleration equation we could write. It looks like this. v1 equals the initial velocity, notice we have an initial velocity, plus the acceleration in the horizontal direction times t1. So these are the three equations we need because look, we've got the acceleration in the horizontal direction, we have the initial velocities, right? We've got the accelerations. And so what do we have? I see three equations and three unknowns, t1, omega 1, and v1, you see? Because of course we know the radius as well. So we should be able to put these equations together, it's just a math problem now, and come up with the amount of time. We wanted it, the rotation rate, but they didn't ask for that, and the velocity once the thing is no longer slipping, right, once it's rolling. And then once we get that, there should be one more kinematic equation that we need in order to determine how far the ball has moved by the time it begins to rotate without slip. What would that kinematic equation look like? Any ideas? When you have accelerations and velocities and you want position instead of time, is there an equation for that? Okay, so we could do that. So we could write v equals v naught plus 2a delta x. That would work. What else could we do? We could also say x1 equals x naught plus v naught t1, not t prime, t1 plus 1/2 ax t1 squared. Choose whichever one you like. It really doesn't matter. Personally, I prefer this one. But I think I went with this one because I knew time. So either or will do. You have an option at this point. Right? So the next thing to do is to plug in numbers that we know. We know all the things I have checked off. Solve for T1 and V1 especially. You could eliminate omega 1 from the equation set if you like. And then, from there, go ahead and plug into these equations, either one, to find the position that's requested. Because of course what you do here is rearrange this to say the change in position is equal to V1 less V0 divided by 2AX. Okay? Okay guys, so let's go ahead and rearrange the equations and solve, because we've got should have everything that we need at this point. Let's see. What do we not care about? I don't care about omega, right? Omega 1. They didn't ask for that. So let's eliminate it in favor of other things. So there's an omega 1 here and here, and that's it. So I guess what I'll do is just plug it in here. So V1 equals, let's see, negative omega 1, but omega 1 is omega naught plus alpha T1. Okay, so now, basically that gets rid of this equation, and really this one, because I've put the two together, you see. So now I've got two equations and two unknowns, because I've only got V1 and T1 with which to contend. I need both of those, so I'll need to solve both of these. Let's see, I guess I'll go for the time first. So if this is V1 equals this and V1 also equals this, then putting those two together, we'd have negative omega naught plus alpha T1 is equal to V naught plus AX T1. So if we put all the, we can come down here because I want to avoid these equations, I don't want to rewrite them. So if we move all the T1 terms to one side, we have negative alpha T1 from this term. Move this to the other side, minus AX T1 equals, on the right-hand side, we'd be left with V naught. We'd have to move the omega naught to the other side, and I feel like I've got a mistake. Oh, I forgot an R. I forgot an R right there along the way. So I need an R here, which means we'd have an R there. Alpha T1 R, yeah, and then we need omega naught R, so plus omega naught R, because if I move omega naught to the other side, it'll become positive. Okay, there we go. All right, so solving for T1, I'd have V naught plus omega naught R divided by all the multipliers. Wait a second. Oh yeah, T1 is what I'm solving for. So that would be negative alpha minus, let's see, AX R. I still feel like something's wrong because, yeah, these don't make sense. What did I do? I put the R on the wrong thing. Anybody caught me? It belongs with alpha T and with omega. So I should have had R with that. So I should have R minus AX. That's better. That should do it. So now we just plug in numbers. The initial velocity is 15 feet per second. The initial angular rotation rate is a positive 9 radians per second. The radius of the ball is just 1/3 of a foot. Notice the radians go away for free, so in the numerator we just have feet per second. In the denominator we need negative of, let's see, alpha, but alpha is a known number. It's negative 24.15 radians per second squared. R is still 1/3 of a foot. And then we also have to subtract off the acceleration in the x direction, which is a negative 3.22 feet per second squared. Okay. Now I think that I had both terms the same in the denominator when I solved this. So maybe I've also made a sign error along the way. Some more from memory. Yeah, they are the same sign. So what have I done here? Let's see. Probably tried to go too fast in the algebra. Let's see. So we got V1 equals omega naught, or negative omega 1, but that's omega naught plus alpha T1. That's okay, terms R. I'm all right with that now. V1 equals V naught plus AX T1. That's okay. Put the two together. Negative omega naught alpha T1 R equals V naught AX T1. That's okay. So then, moving down here, I put this term first, which is negative alpha T1 R. That's okay. And then goodness, what did I do? Oh, I was pulling terms. That's right. So pulling this term to the other side, we have negative AX T1. That's fine. And then V naught over here, this is a negative omega naught R. Move to the other side, it becomes positive. Let's see.
Why did you add the second negative on the bottom of the very outside the parentheses?
Oh.
That negative, is that supposed to be there?
I don't think so. But it should be here. Because look, alpha is itself a negative thing, and that negative sign goes with this term. So basically this becomes positive, and this becomes positive, and that's what I was looking for. There we go, thank you. So T1, we plug in all the numbers. This should be consistent. We got feet per second squared, feet per second squared, feet per second in the numerator. All the feet go away. And then seconds squared over seconds are just seconds. So T1 comes out to a time of 1.5971 seconds. So that's how long it takes for the bowling ball to start rolling without slipping. Once we have that, it's pretty easy to plug into anything else we want to know. For example, if we want to know the velocity at that point, just plug in T1 here. We know alpha, that was our solution, negative 24.15. We were given omega 9 radians per second. Radius of the ball is known, so that's easy. In fact, let's just go ahead and take care of that part. Don't need any of this anymore. So negative, let's see, omega naught, 9 radians per second plus alpha. Well, alpha is a negative thing, so let's write minus 24.15 radians per second squared times 1.5, we'll run out of space, 971 seconds, that'll take care of that. We need to multiply this by r, so 1/3 of a foot. Sorry, that's off the video, but all right. So the radians will go away for free. We've got well, actually that goes there, doesn't it? Because r is outside. So we got 1/seconds multiplied by 1/3 of a foot. Looks like we'll get a negative number. And I was thinking we should get positive. No, this is going to be large. Yeah. So, let's see, we won't, I don't think we'll need that anymore either. So V1 with these numbers, make sure that I'm being consistent here. Yeah, I got 9.857 feet per second. Somebody double check me on that, make sure I haven't made a mistake. That should be fine. I actually calculated omega 1 that way, but it doesn't matter. And then we can take our pick. Which one do you want to use? This one or this one? I used this one. For fun, why don't we try the other one? See what happens. I know, I have an odd sense of fun. It's okay. Since I've already rearranged it, let's just use it. The change in position should be the initial velocity, not the initial velocity, the final velocity, 9.857 feet per second, minus the initial 15, these are both feet per second, divided by 2 times the horizontal acceleration, which is negative 3.22 feet per second squared. And you notice that we have something that doesn't make any sense, because I shouldn't get seconds out of this. Feet per second, what did I do wrong? I should get feet. Check units, feet. Oh, it should be squared, shouldn't it? There we go. So let's try that. So I need to square each of these terms. And that would mean these units are squared. See, units save you. See that? Love units. We need to love them too. So there we go. Take 9.857 squared minus 15 squared, divide by 2, and divide by negative 3.22. You should get what I got from the other equation, is about 19.85 feet. Okay? Any questions about all that? Did it come out this way? Does that work? This equation? Questions, comments, anything?